All right, this is our bread engineers report. Our CSS team is Autumn, Emily, and Jess, and our ITESO team members are Karina, Juan Carlos, and Ana Sofia. The purpose of our project was to solve this problem for Pan Vital, a bakery in Duluth. They've asked for assistance in maximizing their in-house yeast production. So our goal was to analyze the growth kinetics of yeast and propose a plan to increase biomass production for Pan Vital.
Our methods at CSS to analyze the growth of yeast was to create a yeast culture and add that yeast culture to cranberry juice and glucose, and to test every 15 to 30 minutes in order to see how the glucose has been used up and how much the yeast has grown. We measured how much yeast we had by UV vis and taking the absorbance and using that for concentration of yeast. And for the concentration of sugar that's left, we used refractometry with bricks in order to determine the overall concentration. And now over to the ITESO stuff.
And then very similarly, our team at Ateso did an experiment that included also making a yeast culture, adjusting the pH, adding glucose and cranberry juice, and then reacting it and doing UV vis in addition to a glucose oxidase enzymatic kinetic test, which in turn measured the relationship between glucose concentration and absorbance. And also they were able to obtain a calibration equation to quantify glucose in unknown samples. And then just a note about some conditions influencing these yeast kinetics. Temperature is very important, and in addition to ensuring proper mixing occurs and aeration is also occurring. Then we will throw it over to the Ateso team to talk a bit more about the results and recommendations based on these.
For the growth phases of yeast, both ITES and CSS observed the same three stages. First, the lag phase, where the cells adjust to the medium. Second, the exponential phase, where growth increases rapidly. And third, the stationary phase, when nutrients decrease and growth levels off. These phases help us identify when yeast produces the most biomass. Same here for the substrate, and here also we can see the three phases. Then from these growth curves, we calculated the maximum specific growth rate, that is the mu max. For ITESO, which worked with three reactors, reactor 2 showed the highest maximum mu max at 0.366 per hour, while reactors 1 and 3 had 0.143 and 0.136. For CSS, which used one reactor, the mu max was 0.182 per hour. We then compared the GLI indicators, that is the biomass produced per sugar consumed, and the KS. In ITESO, Y-XS values were 0.48 and 0.105 and 0.36, and the average KS was around 4, meaning a lower affinity for the substrate. And in CSS, the single reactor had a much higher Y-XS of 0.95 and a lower KS of 1.5, indicating more efficient sugar utilization. Then, based on this, we proposed two recommendations for Pan Vital. First, control temperatures between 27 and 37 degrees Celsius, since too much heat harms the yeast and too little slows growth, depending on which yeast you use is the temperature you should use. And second, ensure proper mixing, because several outliers came from poor homogenization, and good stirring improves nutrients distribution and measurement accuracy.
And to recap, we successfully characterized yeast growth kinetics in cranberry juice, identified all three growth phases, determined maximum specific growth rate values comparable to literature, achieved yields up to 0.95, and generate practical recommendations for Pan Vital Bakery to optimize their in-house yeast production. Thank for your attention.